Hey, Wheat North, Mr. Yurgler here. We're going to pick up where we left off with the last video, which was just an overview of all the different types of reactions. Now we're going to dig into double replacement reactions more specifically, and then talk about ionic equations, net ionic and complete ionic equations. All right, let's get started. This is kind of where we left off, talking about what a double replacement reaction is. In a double replacement reaction, we're just switching the anions. You could think of it as switching the anions, and that's what this picture shows. You could also think of it as switching the cations as well, the positives, and leaving the anions where they are. Either case, we're just exchanging the ions. There's no change to any of the charge. They're all just staying the same. They're just switching partners. This picture does a great job of illustrating that. We start with reactants, there we have our products. So our reactants are just switching partners to form our products. All right, let's do a quick review of what aqueous means, because this is always going to be happening in an aqueous solution. Whenever you have an ionic substance, this could also be referred to as a salt, right? So salt doesn't just refer to sodium chloride, it refers to any ionic compound. So when any ionic compound dissolves in water, the solvent, the water molecules, actually pull the ions apart from each other, right? So you have individual ions floating around. You don't really have the solid, the actual molecules anymore. That's different from a molecular, covalently bonded molecule dissolving in water or mixing with water. Like if you think about alcohol, alcohol mixes in water, but it doesn't form ions because it's all nonmetals. It's all covalent. It just has a polar end of the molecule that the water kind of grabs onto. That's different. When an ion dissolves, it's literally the ions are literally pulled apart from each other. Here's the most common example: sodium chloride dissolved in water. Notice what's changing about the phase notation. We're starting with a solid, so that's the actual white crystal that you're familiar with. When that dissolves in water, it becomes aqueous and it becomes separated, right? So we have sodium ions and chloride ions floating around. This is considered an electrolyte, so it conducts electricity when it's in water because we have those charged particles. Here's a great picture that kind of shows that too. What I love about this picture is it's trying to be very accurate and it pays attention to details. So if you look at the relative size of the sodium versus the chlorine ion, they're different, and that's intentional. If you look at how the water molecules are arranged around each ion, in this case we have a sodium ion, so that's the positive. So we have the negative end of the water molecules kind of angled towards it, right? The oxygen end is negative, the hydrogen ends are positive. If you look at the chlorine atom, or I should say ion, then the positive ends of the water molecules are oriented towards the ion. That's a really realistic way of representing this, because this is how we understand the dissolving to happen, is that the positive end of the water molecules grab on to the negative ion, and the negative end of the water molecules grab on, so to speak, to the positive cation. All right, here's another particle picture. It kind of shows the same thing, just not quite as clearly. We have cations and anions in there. And I kind of want to come back to this picture here. This isn't actually what's happening, right? This is a little deceptive. It's really good at showing the process of the double replacement reaction, but it's not really showing how this actually works. This image is kind of showing the partners as kind of bound together, and then they quickly switch partners, right? Well, this is aqueous, and so we don't have the cation and the anion together at all. They're floating around in the solution. When we form a solid precipitate, which we'll talk about in a second, we have a positive ion linking up with a negative ion, right, to form a solid that's not soluble in water. All right, so let's talk about that. Whenever we form a solid, when we have two aqueous solutions and they combine to form a solid, we call that solid the precipitate. And that's whenever we have the two ions that are going to be more attracted to each other than they are to the water, right? So the water essentially is unable to pull them apart. If all the products are aqueous, if everything is aqueous and nothing is insoluble, then we say that there's no reaction, because there's no physical change, there's no color change, there's nothing like that that can be formed, because everything's still dissolved. It just looks like salt water still. We can separate these two parts by what's called gravimetric analysis. You would want to take your mixture of your solution and precipitate in your beaker, pour it into a funnel. You can use a stirring rod to kind of make sure you don't drip down the side. It's a good technique that is commonly used. Filter paper captures all that solid, and then we would maybe often dry it in an oven until constant weight in order to make sure that we've got all the water out and to weigh our precipitate that was formed. All right, let's talk about molecular versus ionic reactions. A molecular reaction is what you're used to, where we have our two reactants forming our two products in a double replacement reaction. The ionic equation is a little more precise in what it's representing. It shows that our solution actually doesn't really contain lead nitrate per se. It contains lead ions and nitrate ions, right? And potassium ions and iodide ions. Now, pay attention to this. The solid that's formed is represented in the ionic equation as together, right? So all of these are aqueous ions. They're still floating around in there. The lead iodide, though, has formed a solid, and so we show that as together because it is no longer an ion. It is now together. This is what we would call our complete ionic equation. It's showing all of the ions that are present in the solution. What we often want to use, though, because that complete ionic equation is kind of cumbersome to look at, we often eliminate what are called the spectator ions, and we only focus on what's undergoing a change. So staying with that same example, I've color-coded this to kind of make this pop out a little bit more. Notice that I have nitrate ions on both sides, so nitrate's not changing, right? It's called a spectator ion. We can cancel it out. The same is true of potassium. Potassium isn't doing anything. It's dissolved before the reaction, and it's still dissolved after the reaction. So our net ionic equation is just our lead ions and our iodide ions are coming together to form a solid lead iodide precipitate. And this is actually that yellow precipitate that you saw at the very beginning in that picture on the very first slide. All right, let's get a little practice. Write a complete ionic equation of silver nitrate plus potassium chloride produces silver chloride and potassium nitrate. Pay attention to what our precipitate is and make sure you're representing all of the ions that are in the solution. So the complete ionic equation first. Go ahead and pause the video and write that out. All right, now that you have that written out, let's write the net ionic equation. So rewrite it, but eliminate all of the spectator ions. If you want to, if it's helpful to cross them out, then do that. The net ionic equation is always going to be much shorter than the complete ionic equation, of course, because you've crossed out all the spectator ions. All right. Bring that complete ionic equation and your net ionic equation to class. Make sure you're writing down any questions if you're confused at any point in this video, and we'll talk about that in class. All right, this is Mr. Yergler signing out.